Hello everyone. So today we're going to continue on chapter 12.2 linear system. So what I want to do today is simply just give you a few more examples on solving this system using elimination method. All right, so let's try another example. So this one will be a little tricky because this one is actually a second order linear system. Oops, sorry, X. So in this case, we have a second order differential equation, a second order system of differential equation. However, this one is nice in the sense that it does not involve the first derivative. So therefore make it easier for us to actually solve this system. So if it does involve the first derivative, it will definitely make it a lot harder to do. So we're going to try to do the exact same thing. We're going to try to use the elimination method to come up with the solution. So this would actually take a while. So hopefully, let's see. So this become x double prime equal to x plus 2y plus t. So therefore become x double prime minus x minus 2y equal to t. So I can say d squared minus 1 of x minus 2y equal to t. So this one become y double prime equal to 3x plus 2y. So therefore I'm going to say negative 3x plus y double prime minus 2y equal to 0. So therefore become negative 3x plus d squared minus 2 of y equal to 0. So now I have my two equations in differential operators form. All right. So look pretty good. And so now what I'm going to try to do is try the elimination method. So I'm going to go and write down my first equation. And here's my second equation. So to eliminate, so once again, it's really up to you which one you want to eliminate first. I don't have a preference. I guess we can eliminate x again and see what happens. Okay, so we're going to do that. So what I'm going to do is I'm going to multiply the first equation by 3. I'm going to multiply the second equation by d squared minus 1. So the first equation becomes 3d squared minus 1 of x minus 6y equal to 3t. The second equation here becomes negative 3d squared minus 1 of x plus d squared minus 1, d squared minus 2, y equal to 0. And so now I can take these two things and add them. And when I do that, the x would cancel out. And now the y will become d squared minus 1, d squared minus 2 of y minus 6y equal to 3t. I'm not going to put down d squared minus 1 of 0, which is just 0. So therefore that's gone. So let's see if we can figure this out. So if I'm looking at this correctly, that becomes d to the 4th minus 3 d squared plus 2 y minus 6y equal to 3t. And so move the 6 in, become d to the 4 minus 3d squared minus 4 of y equal to 3t. And this actually can be factored into d squared minus 4 and then d squared plus 1 of y equal to 3t. And then d squared minus 4 can be further factored into d minus 2, d plus 2, d squared plus 1 of y equal to 3t. So that become my differential equations. And once again, this one is not too difficult to solve. It's a non-homogeneous differential equation. There are multiple ways to do this. So we can definitely try to do this. So the method that I'm going to use is the following. I am going to try to use undetermined coefficient method. Oops. Okay. So what I need is an annihilator that can get rid of 3t. So it should be pretty simple. That would just be d squared. Because if I take a derivative once, that would be 3, and then take it again would be 0. So therefore I can say that d squared times d minus 2, d plus 2, times d squared plus 1 of y should equal to 0. And therefore our solution y should have the following general solution form: c1 e to the 2t plus c2 e to the negative 2t. So that's from d minus 2 and d plus 2. D squared plus 1, it has two imaginary roots, which are plus or minus I. So therefore would generate c3 cosine t plus c4 sine t. D squared will generate two other roots, which will be the undetermined coefficient that we try to figure out, and that will be c5 plus c6t. Because that will be e to 0, and as repeated roots would be t e to 0, which is t. So therefore, we know that these would be my homogeneous solution. So that would have to be my particular solution that we try to figure it out. So let's try to figure it out. So y sub p would be c5 plus c6t. And so that's actually pretty simple, because then y sub p prime would be c6, and then y sub p double prime is equal to y sub p triple prime, which is equal to y sub p to the fourth derivative. They're all 0. So therefore, my fourth order differential equation, it really sounds like complicated, but actually not too bad. So I'm going to go and plug it in to solve for my differential equation now. So therefore, what I have will be this, is d to the fourth minus 3d squared minus 4 of y is equal to 3t. Yep, 3t. And so if I plug in y sub p, actually I'm going to put y sub p, so therefore it becomes 0. Oh, actually, so it becomes 0 and 0. So therefore it just become negative 4 times y sub p, so become negative 4 c sub 5 minus 4 c sub 6 of t equal to 3t. So therefore imply that c sub 5 must be 0, and negative 4 c sub 6 must equal to 3, indicating c sub 6 must equal to 3 over 4, negative 3 over 4. And so therefore give us our answer for y. Our answer for y is c1 e to 2t plus c2 e to negative 2t plus c3 cosine t plus c4 sine t plus c5, which is 0, plus c6 times t, which is negative 3 over 4t. So we got y. So that's not too bad. So now let's try to find x. So once again, when you try to find x, you try to pick an equation that does not require you to do differential equation again, and that would be this equation right here, the second one, which is also nice because homogeneous. So therefore, what I have would be this. So let's see. So here's the equation. Negative 3x is plus d squared minus 2 of y is equal to 0. Let me see, double check. Yep, that's it. So now that we know y, we can go and try to figure this out. So instead of writing it out into it, I'm going to just write out the second derivative y first, so that way it's easier to do. So y is c1 e to 2t plus c2 e to negative 2t plus c3 cosine t plus c4 sine t plus negative 3 over 4t. So y prime would be 2c1 e to 2t minus 2c2 e to negative 2t minus c3 sine t plus c4 cosine t plus negative 3 over 4. And then y double prime would be 4c1 e to 2t plus 4c2 e to negative 2t minus c3 cosine t minus c4 sine t plus 0. So now I think I'm ready to go ahead and solve this. So negative 3x plus d squared minus 2 of y would basically be 4c1 e to 2t plus 4c2 e to negative 2t minus c3 cosine t minus c4 sine t minus 2c1 e to 2t minus 2c2 e to negative 2t. Remember, I have to distribute negative 2 to y. Minus 2 cosine c3 cosine t minus 2c4 sine t plus 3 over 2t equal to 0. So that looked like a lot of things going on, but remember, one of the nice thing about solving this system of solving differential equation like this is that terms just combine together. So I'm going to keep the negative 3x. I have 4c1 e to 2t minus 2c1 e to 2t. So seem to me I will get 2. So plus 2c1 e to 2t. Same thing with this one. I have 4c2 e to negative 2t minus 2c2. So it becomes plus 2c2 e to negative 2t. Cosine t seem to me that will be minus 3 of them. Minus 3c3 cosine t. And there will also be 3c4 sine t. And then I just have the plus 3 over 2t equal to 0. So seem to me, I have to remove everything over and then divide it by, or move the negative 3x over and divide by 3. So therefore x would equal to, seem to me is 2/3 c1 e to 2t plus 2/3 c2 e to negative 2t minus c3 cosine t minus c4 sine t plus 1/2 t. So that seems to be what my x is going to be. So therefore, now I can put them together and form my solution. xy is going to be equal to c1 e to 2t and then 2/3 1 plus c2 e to negative 2t 2/3 1 plus c3 cosine t multiplied by negative 1 plus c4 sine t multiplied by negative 1 plus 1/2 negative 3 4 t. So that seemed to be my solution. Now, one thing I do want to point out is the following. Because of the C1, C2, C3, and C4 can be any arbitrary constant. The four vectors here can actually be multiple. So therefore, it's actually all perfectly okay if you write your answer like this. Now, the only one that cannot change is this last one right here. As you notice that this last one doesn't have an arbitrary constant C5 connect to it. And the reason why, because this is actually more like the particular solution in a non-homogeneous differential equation. So that one doesn't have arbitrary constant and therefore has to be unique. While these first four are kind of from the homogeneous solution, so therefore can be actually any multiple. So if you want to write it without fraction for the first, at least for the first four, you could do so by doing that. All right, so that takes care of this one. So now go ahead and show you one more example. Okay, so this one will be this. Solve. Dx over dt plus dy over dt equal to 2x plus 4y, and 2 dx over dt plus 3 dy over dt equal to 2x plus 6y. So now notice that this one is a little different compared to the last two that we have done. The last two that we have done, we have dx dt equal to something and dy dt equal to something. But this one is tricky in the sense that we actually have dx dy together in two separate equations. So what you first have to do is to put this equation into kind of the normal form first. So how do we do that? Well, the way to do that is try to isolate dx dt and dy dt first. So meaning before you even get to solve the system of differential equation, we kind of have to set up the system of differential equation correctly. So what I'm going to do is the following. I am going to multiply the first equation by -3. And the second equation I'm going to keep exactly the same. And then I'm going to add these two system equation together. Notice that the dy will cancel out. That gives you negative dx over dt equal to negative 4x minus 6y. So therefore dx over dt must equal to 4x plus 6y. So that takes care of dx over dt. And so now I'm going to try to solve for dy over dt. So it's pretty simple. I can simply say this. We know dx over dt plus dy over dt equal to 2x plus 4y. So therefore meaning dy over dt must equal to 2x plus 4y minus dx over dt, which is 4x plus 6y. So therefore, dy over dt should equal to negative 2x minus 2y. So now that we have these two equations, now I can try to solve it. So let's see if we can go through this. So the first equation is dx over dt equal to 4x plus 6y. So therefore meaning is x prime equal to 4x plus 6y. Therefore equal to x prime minus 4x minus 6y equal to 0. That is d minus 4 of x minus 6y equal to 0. My second equation, dy over dt equal to negative 2x minus 2y, so therefore become y prime equal to negative 2x minus 2y. So if I move it over, they become 2x plus y prime plus 2y equal to 0. That means 2x plus d plus 2 of y equal to 0. So that become my 2 equation. So this time we try to get rid of y instead. So I'm going to take the top equation and the bottom equation. We'll take the top equation and kind of apply d plus 2 to it. We'll take the second equation and apply 6 to it. So the first equation becomes d plus 2, d minus 4 of x minus 6d plus 2 of y equal to 0. The second equation becomes minus 12x plus 6d plus 2 of y equal to 0. When I add them together, these two things cancel out. And so all I have is d plus 2, d minus 4 of x minus 12x equal to 0. And so that will be d squared minus 2d minus 8x minus 12x equal to 0. So therefore become d squared minus 2d minus 20 of x equal to 0. Now that is interesting because that does not come out to be factorable. Let me double check my math, make sure I didn't do anything wrong. Oh, yep, actually I did make a mistake right there. That's positive 2x and I have a negative. So let's fix that. So that becomes plus plus. So that actually becomes plus 4. Alright, so I think that fixed the mistake. So now that becomes an issue right here because that is also not factorable. Not only not factorable, but this, I would imagine this come out to be imaginary. So let's see if that's the case. So am I looking at this correctly? If I now say d squared minus 2r plus 4 equal to 0, that's our characteristic equation, then r should equal to negative b, which is 2, plus or minus square root of b squared, which is 4, b squared minus 4ac, so 4 times 1 times 4, which is 16, over 2. So that come out to be 2 plus or minus 2 radical 3 over 2, or 1 plus or 2i radical 3 over 2. So it become 1 plus or minus I radical 3. So that will be my two characteristic roots. And so in that case, that would mean that x should equal to c1 e to the t cosine radical 3t plus c2 e to the t sine radical 3t. So that seems to be what our x is. Interesting thing to note in this case, notice that our x is a homogeneous differential equation, and mainly because our system doesn't have the vector b. And if you put 1 and 1 together, you probably realize that when you have no vector b, you will have what we call a homogeneous linear system. So we'll talk more about it when we get to chapter 13. Okay, so now we found x. Now we just have to find y. So y, we can definitely use this equation right here to find y, because that would require me to take the derivative of x only. So we can definitely do that. So dx over dt is actually equal to 4x plus 6y. So therefore, meaning the following. So if I take the derivative of this thing, so that actually not that easy to do. So maybe I'll just write out the derivative of this thing first. So what is x dx over dt, or x prime? So that would be c1, 1d2 plus 2d1. So 1 d2 plus 2 d1, which is just stays the same, plus c2 1 d2 plus 2 d1. Okay, so therefore seems to me that dx over dt is equal to negative radical 3 c1 e to t sine radical 3t plus c1 e to t cosine radical 3t plus radical 3 c2 e to t cosine radical 3t plus c2 e to t sine radical 3t. So that's a lot of things. So let's see if we can figure this out. So therefore, that is actually also equal to 4x plus 6y. So let's write them out. Oops, cosine. Is equal to 4c1 e to t cosine radical 3t plus 4c2 e to t sine radical 3t and plus 6y. So it seems to me what I'm going to do is just simply subtract this to the other side. So let me see, c1 e to, so that would combine with this term right here and become negative, I guess. So negative radical 3 c1 e to t sine radical 3t minus 3 c1 e to t cosine radical 3t. This radical 3 c2 e to t cosine radical 3t stay, and then minus 3 c2 e to t sine radical 3t equal to 6y. And so what I'm going to do is simply divide by 6. And then when I divide all of them by 6, then I would have what I need. So let me see. So let me see. So it seemed to me that y would equal to, I'm going to try to see how I'm going to collect all these terms together. So seem to me I have c1, c2. I'm going to collect all the c1 e to the t together. So therefore it will be c1 e to t multiplied by negative radical 3 over 6 sine rad 3t minus 1/2 cosine radical 3t. So those are the two terms that were c1 e to t. The reason why I want to do that because then that would match with this c1 e to t right here. And then I'm going to do the c2 e to t. So plus c2 e to t. And then what I have is radical 3 over 6 cosine radical 3t minus 1/2 sine radical 3t. So that would be my y, and that would be my x. So now I can combine them together to form my solution. So my solution would be this. X and y would equal to c1 e to t. And then for x, all I have is cosine radical 3t. And then for y, I have negative radical 3 over 6 sine radical 3t minus 1/2 cosine radical 3t plus c2 e to t And then for x, all I have is sine radical 3t. But for y, I have radical 3 over 6 cosine radical 3t minus 1/2 sine radical 3t. So that seemed to be my answer written into a vector form. So unfortunately, that's all the time I got. So I only get to go through these two examples with you. So there are plenty of homework problem in chapter 12.2 for you to try out. It will take some practice to do some of these questions correctly. As you can see, there's a lot of things going on that you can make mistake on. So that will be it for 12.2. All right, I'll talk to you in the next video. Bye-bye.